Okay, welcome everybody to my talk, Real-World Analytics with Solr Cloud and Spark. I have a little bit technical problem here, as you've seen with my cloud case, but nevertheless, I can give you an overview of how this is actually working to build real-world applications on top of this both open source tools. To understand what the talk about today is the problem we want to solve. I'm not a data analyst. I don't write batch jobs for in clusters, in big data clusters, and analyze, do long-term analysis. What I really want to do is write interactive applications with fast runtimes. And such runtimes should be between a second, sometimes a little bit longer, but it should give the user to explore, to do interactive analysis. And that's a special problem for most applications. But if you want to make business applications and to make business decisions, you have to have very fast tools. You can't do a Hadoop job and wait until tomorrow. That doesn't work. This is like the 60s, in the 60s, where we have batch jobs overnight, and now we want to have fast interactive applications. And the scope I want to focus today is how to process billions up to trillions of records. I really know that many people thinking about big data are talking about much more data than this. But I will show you some idea of how to compress data in rows and expand it on runtime. This actually works up to 1 trillion of records very fast. Until then, you can't get results in a second or so. The import should be constantly. I will import constantly data in such an application near real time. Near real time depends on the scope, and maybe it means 10 minutes, maybe it means 1 minute. Maybe it also means an hour, but it never means writing an ETL job overnight, which imports the new data once a day. And we all are developers today facing the problem of cloud computing. We want to have resilient applications, which means that they are fail-safe. If one node goes down, the application works well. We want to have scalable applications to give the opportunity of horizontal scaling. And we want to have responsive applications, which mostly mean they have to be asynchronous. And here in the reactive manifesto, it's called event-driven. So writing such an application can be really, really hard. And there are a lot of frameworks out there, but they are very, very low level. And for most businesses, you can't afford to build things like Netflix did, Twitter did in a normal enterprise. I work a lot of time in Munich for a car manufacturer. Guess get the name. And the budget is not so high to build frameworks from the scratch. We have to really select pre-integrated frameworks and tools to build applications which give the power to make them competitive with the Silicon Valley automotive industry. These are some screenshots of applications. On the upper corner, on the left side, you see application we built for application performance monitoring. The backend, the storage engine is already open source. It's called Chronix.io, and it's based on Solr and Spark. The same story I talked today. And this application is an expert analysis application. What does it mean? It means we collect every 10 seconds all metrics we can get available from a microservice or JE server. Or if you have a WebLogic server, for example, you can get more than 10,000 metrics out of the box from this server, like connection pool states and transaction states and everything, threading, memory. And these informations can be valuable if you want to find out what is the root cause of a problem. If the users can't work, maybe there's a technical problem with the disk, maybe there's a technical problem with the network, and how do you find it out? You have to have a holistic view. And if you record for one single JE server 10,000 metrics in 10 minutes, in 10 seconds, and you say you have 10 servers in production, then you get really 1 billion of unique metrics per day. And this must be stored. We don't want to compress the data much. We don't want to lose information, because maybe we have to we have to look at the exact point where the problem starts. And most monitoring tools out on the market can't do this. They're making monitoring. They don't making problem analytics. Other examples here for such applications are careerfinder.com, which is quite common. It's built on Solr. And if you look at such a dashboard, I've seen in my career a lot of dashboards like this, which they have developed with SQL. And this actually does not work. You have to have an analytics engine which gives you the power to build such aggregated informations very fast. Google Analytics is also a very well-known example. Hue dashboard and many other dashboards. These are the applications I want to focus today. And the problem with such applications is that the scaling can be very difficult. We all talk today about microservices, but what's really trivial is to have a load balancing of stateless services. It's trivial. It's well understood. We do this since the early 2000s. We had hardware load balancer, we had software load balancer, but the key point is that everything is stateless, and then it's really easy, and you can add more machines for more users. But what's really hard is to get faster response times. If you want to have an application where you add servers and get, for a single user, faster response time, things change. And things are not so easy. It's not a single microservice anymore. You have to distribute your load for a single user in the cluster, and that's not trivial. Also, from the data side, if you want to horizontal scale your data, what's also very well understood is linear distribution of data on multiple machines. That's, I remember when I studied computer science more than 20 years ago, we had a script and there were distributed databases, and this concept is very old. Now in the new SQL world, we have a lot of choices, but only distribute the data is only one thing. The problem is if you have constantly growing data and you want to have constant response times. And that means you have to also to process the data in parallel, and not only store in parallel. And that makes things really, really difficult. And 10 years ago, Hadoop has birthday this year. And 10 years ago, Hadoop gives an answer for an idea which was revolutionary at the time. And the idea was how to store data in a distributed way and process the data also on the distributed nodes. And the idea was revolutionary. That's the reason why everybody knows Hadoop, I think. But the problem here was it was much, much too slow. This was much, much too slow. And there's a main point for this. And even if you try today Spark and try to write an application with Spark, the first thing in any book I read about Spark is, in my opinion, the big data anti-pattern. And the problem here is the following. Every big data technology focuses on distributed storage and distributed processing today. And we have, for example, HDFS, the Hadoop data file system, or any NoSQL database like Cassandra. And storing data in a distributed way is easy. It works out of the box. Then, with Hadoop and also with Spark, you read things in memory out of disk. And the first thing you learn is, oh yes, Spark has a very, very good parallel filter possibilities, so you can filter in parallel and can process the data in a maps step to get your result to make a dashboard, for example. And this is very, very slow, because if you implement this with huge data sets, you have to read much, much data, even if you only want to have a slice of your data for the user. For example, if we build applications for the automotive industry, the normal user which make the business, they are responsible not for everything in the company. They are only responsible for say, the BMW i5. And if they can grab only this results very fast, it works much, much better. And searching is the key point here. And that's the reason why we have the buzzword search-based BI in the last years. And it goes up and down, how does it actually work? But one key feature of searching is that you have an index data store. And this can be done with a search engine like Solr or Elasticsearch. And it can be done with a NoSQL database. But many of the NoSQL databases like MongoDB or others have some limitations in searching. They are not designed for indexing. They're not indexing machines. And if you have a search access, you can search and you have much, much less data to process. And the filter step could be removed. So searching is really the key to get fast results and to get pre-aggregated results. And then you do a map. You do the map step and process everything together in a reduce step to your chart, to get your chart. This works actually quite well, and this means you have to have two things. You have to have really, really fast searching and index data, and you have to have you must process the data in parallel. Otherwise, you will get stuck if the data is if the search result is big. The maps step will be a bottleneck if it's only runs on a single machine. And in this talk, I will focus on this technical infrastructure. I'm sure that there are other choices as well, and maybe they work better or even the same way. But it's more a pattern for designing applications which read mostly and write seldom. And most of the business applications I programmed and designed in my career have more search use cases than transactional use cases. So searching is really, really the key feature here. And if you have the search result now in a cluster, like a Solr Cloud, you can process these results in Spark in parallel. And that's a nice thing. And can get the results to a normal JE application, for example, or a Spring application, a Spring microservice, which collects everything together and gives JSON answer, REST answer to your client. I have some samples here of frontends which are written in JavaFX or HTML5. Everything is possible here, I think. Okay, let's look in depth about Solr. Solr Cloud for Analytics. I think everybody here in the room has heard about Solr and used it in some way. But most people I know say, oh, Solr is a search engine and I can put a text field in my web application and that's Solr and it's okay. And I have a Lucene search index and everything is fine. And I index a database or I index a file store and now I can search rapidly. I have some concepts of text analysis in Solr and it's a classical enterprise search engine. But that's not actually true. That's only one point of the story. I would say, and the interesting thing, there are only few people in the web which exactly describe Solr this way. That's not quite common. I would say it's a document-oriented NoSQL database with focus on search. And that is the business case of the company behind Solr. They have a commercial product with use Solr as NoSQL database as well. That's not only text search. And we will see you can do a strong, you can build rock solid enterprise applications and use it as a NoSQL database with sharp search, not unsharp search. The thing here is that a document is a collection of fields and they have types and can be arrays. And that's a very, very powerful feature. You can put an array field in you can put an array in a single field. and search over that. And you can nest documents, and a thing which is other than Elasticsearch, Solr has a static scheme. You can use a dynamic scheme, but the most applications I've written with Solr use a static scheme like a database scheme in a relational database. You have a powerful query language, and the main thing here is it scales. It scales with Solr Cloud, and Solr Cloud makes it easy to distribute your data in separate shards, distribute in a cluster, and make it resilience. And make resilience by Zookeeper, by using Zookeeper, and replication. I show a picture. And the thing here I will show you in a demo now is Solr has powerful aggregation features, which comes with the Facet API. And most people know facets from web application, where you can see the products, the count, how many products are available of this type. That are typical count aggregations, but Solr can do much more, like statistical aggregations, average, minimum, maximum, and so on. Okay, and it's stable. That is an interesting slide, I think, that should be well understood. You have the Solr Cloud, which consists of several servers, and the server configuration is in Zookeeper on the top. And normally the Zookeeper has one leader elected. That's typical Zookeeper behavior. And from this leader, the configuration will be distributed in the Solr servers. And we have a collection here of shards, and when you look, we have one replica. What does it mean? It means that one Solr server can shut down, and every shard is available, stays available, because we have the replicas for every shard replicated here. Okay, why the NoSQL database? Why is this a NoSQL database? If you look in depth, you will see that everything is like a single table, like the Google Big Table approach, which was documented in a paper 2003. And if you have this kind of data model, we have a customer with orders, and it's a one-to-many relation. And the customer has the name, and the orders has amount and product. You can store this very easily in a single table like this. You have to add a type descriptor field, and the type descriptor field gives you the opportunity to build tables per design. When you filter per type, you get all records from the customer table. If you filter per order, you get all orders. With IDs here, then we have the union of all fields from all tables, and you see the relation mapping customer to order, which is a multiple field and can be used to join. Solr supports in a special way joins, but for big data, if there are billions of records, you can't join data directly in Solr. And I show you approach how does it work in detail. Okay, if you build such an application in one shard and store the records in one shard, you can normally store about 100 million in a single shard. Now you have to know that one machine don't stores only one shard. It stores as many shards as you have CPU cores. The reason for that is why indexing and searching takes time, and it could be, and the perfect parallelization degree is when every core has its own shard to search, to index. So in this cluster, in my cloud case, I have 4 Intel NUC PCs, and every PC has two cores with hyperthreading, 4 cores. So I can use 16 shards in such a hardware architecture. And 16 shards with 100 millions of documents. And that's 1 billion of documents. Okay, let's take some look about the Facet API. And for that, I have a little local demo here. This should work actually. No. If you try the first time Solr Cloud, there's a start script, the example mode -e, which gives you a wizard which asks you how many nodes you want to run locally. I will have 2 Solr servers, and it asks the ports, starts 2 processes, and starts a zookeeper in the background, which must be started standalone in a professional setup. But in a demo setup, this works quite good. Okay, I have used a collection here. I reuse my data. I've already imported data. Now let's look on the Solr Cloud. Here you see the interesting thing. We see 2 port numbers. Everything runs on the same machine. It's the laptop here, and we have two port numbers for the different shards. So I decided to make 8 shards because this is a quad-core processor with hyperthreading. So I can do 8 tasks in parallel very well on this machine. Let's look a little bit inside what's inside this. This cloud, this local cloud, and we have here 9 million of records, and the records are insurance from an insurance company sample from IBM Watson, from the IBM Watson project. And interesting thing is you have the income of people, with the gender, if they are single or married, and from where they come, and things like that. It's very interesting data. And now take some interesting queries. You may not know that this is possible. Okay, let's start with a very simple example. This curl makes a request. On the Solr, we give 0 rows back, no results, only the facets, and I will have the educations. Which educations exist in the data, and what are the count? How many records are affected? And we see that takes for 10 million of records on this machine takes only 283 milliseconds here. And you see the distribution. We have around about 2 million records bachelor degree. We have 2 million college, high school also, 700,000 master, and 300,000 doctors. That sound is not really impressing. Every website you have today shows some aggregations. But the main thing here is this is a single statement, and everything comes back in a package. So it's only one server call, and that makes things really fast. Let's go a little bit further. And as I said before, you could not only do count operations. You can use average, for example, on a field. And now we have the average male income. Why is this the male income? When you look at the query, we make a query with gender M. That's the male income. Okay. And the male income, we have 4 millions roundabout males in the database, and the average income are 30,700. 37,000. Yes. Okay, now look at the professions. Which profession gains most? We do a facet over the education, so we know what educations are, and do a sub-facet and sum the income for this group. And this works like this. Here are our educations, and here the income. And the interesting thing is here below, as you can see, the doctors gains less than the master degrees, which could be actually real data, I think. Okay, that was 200 milliseconds. That's not bad. Let's make things a little bit more complicated and say, what's the point with males and females here? And I make an additional subfacet with the gender field and calculate the average income. So we see for example, the doctors, and the male average income is 39,000, and the female average income is 45,000. And that's interesting. When you look at the master degrees, you see the males gain more than the females. No, less. Average income 44, but it's no. The females are less than the males. That's average income. But if you have a doctor, you gain more. That's interesting, I think. The last sample to see, you can do facets by using subqueries, and that's a very, very powerful feature for many websites. That means you can group, you pivot, do a pivot facet with your genders, and then group things with the query. The income must be in a range. And so you find everything what's in this range and count this together. Okay, more. Okay, perfect. So you see exactly the count which gains more than 90,000, in the range of 16 and 19, less than 30. We see the masters drill down the females and the males. And for every degree, we have the whole distribution in this bucket. So you can easily think that that's much more than text search, and you can do a lot of aggregations out of the box in the search layer. And the interesting thing here is that this is runs distributed in the cloud. That means if you have multiple machines, the searching, the aggregation, the counting runs completely in parallel in your cluster. And that makes things really, really fast. If you want to read and do this by yourself, I added all the statements I showed in the slides. And okay. The last thing is very interesting. Solr supports SQL. You can do you can use any SQL tool like DB Visualizer, and when you look here, I select the average income from gender from big data group by gender. I can even drill down per SQL. The SQL support is in this new version 6 from Solr is limited. It's not quite ready. It has a lot of things to do, but if this is upcoming this is going better in the upcoming versions, I think it will be a very powerful feature to have a database analysis tool on top of Solr. So resilience, this works even if you shut down one node. And the main thing here is you can do a lot, but not everything. This is not a database for every purpose. For example, you can store images or large binaries in Solr. That does not work very well. You have no interfaces for machine learning, for intelligence features on top. And you can't run your own business logic in parallel in Solr. That works with SAP HANA, but Solr is in this case only as a search database. So that's the main thing. We have to think about something on top. And if you read about Spark, you read is much faster than Hadoop. That's mainly because Spark has a concept of RDDs, and RDDs are cacheable collections, which could be cached in the cluster and accessed multiple times. And that makes things much more faster than reading from disk and writing to disk on every action. Written in Scala, a JVM language, and it's possible to get from every available source data. And also Solr works with the LucidWorks Solr API. This is an architecture slide, and this is not quite common. If you read about Spark, everybody talks about submitting jobs to your cluster, but I will program applications on top, and these applications are driver applications like Zeppelin is a dashboard application from Apache, and my own JE application can use this. Access the cluster by using a Spark context, using the RDDs, which is a distributed collection, and calling operations on the RDD in a functional style, and this transmits tasks to the executor JVMs on the slave nodes, which are started by a worker process. And Spark is very popular. Why? Why you can you don't have to have a cluster. You can do you can get started local, and everything runs here. For example, if I set call this set master local 8 bracket 8, we have 8 executor threads and run things 8 times parallel. And other things, other tasks will be queued if I need more power. That's an interesting thing. You can distribute tasks with params. I use here params. I make a stream of integers, 1, 0, 1, 2. And I call to the Spark context parallelize with this collection, which is a normal Java collection. And it will be distributed in the cluster. And it will be exactly distributed 3 times on 3 different executors, 3 different machines if my cluster is big enough. And then the map task is called and action is executed. That pattern makes it's possible to give every task a parameter, and the parameter will be unique in every task. For example, on the one machine, the parameter will be 0, on the second machine will be 1, and on the third machine will be 2. That's like this. And you can use these parameters to give information in your cluster. For example, how to read from a distributed data source, like a shard. And if you know, so the cluster knows which shards are available, and this runs in parallel. And for one shard ID, there runs only one task in parallel if you do it this way. And the interesting thing here, the shard reader gets, when you look at the read from shard method below, you see that the shard reader gets the shard ID, and it's a unique ID 1, 2, 0, 3, and now it can give you an iterator back on the data which loaded from an external source. And this way the Solr Spark adapter works. And this way every Spark adapter works actually, like when you access Cassandra in parallel or any other data source. And Spark gives you the power to cache results and then reuse the results very fast. Okay. When you will integrate this, you can do it by yourself with the concepts I showed you. But there's also an integration for Solr and Spark from LucidWorks, and this API looks like this. You define a Solr query in the first step. A Solr RDD, the configuration, and then a Solr query, and then call the method query shards. And the query shards method calls everything in parallel and gives you back a RDD. And a RDD is a lazy distributed container, so nothing happens when you until you call the map, until you call the doubles count method, final method action, and then the results are processed. And everything is read in parallel and processed in parallel. Okay, and this example shows you how to make a histogram of exceptions, for example, if you do log file analysis with Solr and Spark. You make a query, you first select the exceptions which may be interesting. For example, I select the exception, every log entry with star exception star, type log record, and from a special host from all production systems. And I map this, I query to a shard, and I get back the Solr documents out of Solr as RDD. And then I map it to a pair. And for each unique exception name, I create a pair with a unique exception name and a 0. And these tuples will be reduced with the reduce by key method by the exception name by adding the values together. And the result is then a histogram of all the exceptions. Yeah. Okay. The last thing here, I had a very nice demos with showing you this actually in this code in action, but I had a technical problem. A cable broke on the airplane. Sorry for that. But if you want to build your own cluster, you can use NUCs like this, and this gives you a very powerful parallel machine. And this is the technical architecture how this actually works with Solr Cloud and Spark on 4 nodes. And you can build such a thing even cheaper with $60 Odroid computers. They don't have the CPU performance like the Intel machines, but this a Solr Spark sample runs quite good there. Yeah. Yeah. And that's the moment when you can process data near real time. These two frameworks are in combination, gives you a powerful tool for analytics. Distributed systems, writing distributed systems is hard. You see distributed systems sometimes fail. But everything is open source, and if you try this in production, it can be quite challenging for high performance applications. Yeah, and you definitely have to look about the Fusion product from LucidWorks. Maybe this helps you to get some integration trouble away, or when you need professional support for this idea. Yeah, please feel free to contact me. And yeah, that's the last thing I want to mention. This is big data technology. I showed you Solr, Spark, Hadoop, and we're all responsible that the software we write are used for a better place and a peaceful world. Thank you very much.